Hello, this is David Bieberman, CTO of Prasaga. Today we're going to talk about the extensible blockchain object model on Hyperledger Fabric. This is a functional overview of it. On the right side of the screen will be a working area. On the left side are slides to help describe what's going on. On the right side of the screen, we're currently showing our GitLab with our current alpha, beta code for the XBOM. This is currently proprietary code. However, we intend to take the class interface layer and make it open source so that everybody can add to this just like you would to any other Hyperledger Fabric system. The extensible blockchain object model for Hyperledger Fabric is layered on top of the Hyperledger Fabric implementation without any changes to it. From the viewpoint of a Hyperledger Fabric node, XBOM is identical to any other chain code. The class manager infrastructure, or CMI, is loaded as chain code on all the nodes that will process transactions. The upper layers are completely transparent to the lower layers of Hyperledger Fabric. The next slide will make that much clearer. On the left side, you'll see what we're now calling traditional chain code on Hyperledger Fabric. The bottom layer is the standard consensus layer in blockchain Hyperledger. So for example, that would be the Raft protocol on an orderer node. Above that is the state database layer, and that will be level DB or couch DB. And then you would load your chain code application to run to do whatever database application you're trying to do. On the right side, we have the exact same, no change whatsoever, blockchain and consensus layer, the exact same layer, the state database layer. And above it, when you load the chain code, it loads just like any other chain code. It is an external chain code, and it's called the class manager infrastructure. However, once we do that, the class manager infrastructure dynamically loads class code in the form of shared objects. And those implement classes. We create a class application framework. And then from that, you instantiate accounts in objects. All of that is transparent to Hyperledger Fabric, so there's no changes necessary to Hyperledger Fabric at all at that point. The blockchain and consensus layer may use any of the consensus algorithms configured for peer nodes and orderer nodes, and the state database is accessed as standard key value pairs. There's no change whatsoever here. Is exactly the same as you would do for any blockchain chain code for Hyperledger Fabric. The next layer up, the class manager infrastructure code is loaded as standard chain code. Now, because from there on in, you can dynamically load class code, the need to load additional chain code on a different channel or trying to put on the same channel for that matter, is no longer necessary. We'll go into how to load chain code. That's what the right side of the screen is for. How to load classes rather on chain code. The CMI, or class manager infrastructure, dynamically loads class implementation code transparently to the Hyperledger Fabric. In fact, these look like regular transactions. You'll see there's a class that does that. These are implemented as Go language plugins, and they're loaded as shared objects. So you have the binary code for them compiled as what's called a plugin mode, and they are loaded dynamically by the environment and distributed dynamically. Once the classes are loaded, the dynamically loaded class implementations create the class application framework by instantiating the foundation classes in objects. And then finally, you now have the ability to instantiate accounts in ordinary objects to provide whatever application space is intended for your classes. And to give a quick overview of what we mean by a first-class object model, which is what the XBOM object model is, the diagram on the left shows the concept of all entities are objects. They're all referenced by an object reference. So you have what's called a meta class object. The meta class object creates classes or class objects, and the class objects create ordinary objects. You can subclass a class object just like you would any other class, and you can actually subclass meta classes to create new types of meta classes that create classes. All objects are referenced by the secure hash 256 hash values. These are used as the keys to the state database. For those familiar with a level DB, it takes a key value pair, and in our space, the key is always an object reference. They're unique values, and we call them LOIDs, or ledger object IDs. They're guaranteed to be unique, so that every object has a unique object ID always. From here, what we are going to do is actually bring up one of the test environments called the test network, which you can find in the standard Fabric samples download for Hyperledger. We're currently implemented on Hyperledger Fabric 2.2. We have run on 1.4, we run on 2.0, we can run on 2.3. At the moment, we're hitting 2.2 because that's got long-term support to it. On the right side, what I will do is run the scripts one at a time to do this. On the left side, I'm going to walk through what the changes are as they're running. And down below, eventually, I'll show some of our log running as well. The scripts that we're running are slightly modified versions of what you'd get out of the test network if you did a Fabric sample download, and we're using all of the Hyperledger code as is with slight configuration changes to support external built chain code. To demonstrate that, I'm going to go up one directory and literally show you that this is in fact the same Fabric samples directory with a handful of things that are specific to us, like the class manager directory. When I go into the test network directory, it looks almost identical, except that we've created our external builder code, and we've taken the network.sh, which is the script that is part of the test network setup, and we've essentially copied it to the class manager script and made some minor modifications to it. We've also done the same thing in the scripts directory, added a couple of scripts, and basically all these are doing is running the pure commands that are necessary to run our environment. And it's slightly different, and I'll show you I'm going to run them one at a time right below this, the screen right below it, you'll see those. So let's start that right now. First thing we're going to do is bring up the network. Before we do that, let's make sure it's down. So it's literally the same thing, that this command is identical to the previous ones, and making sure everything's clean. Now we're going to bring it up, and this is doing the exact same thing. We're bringing up the layers, very first layers. And this point, you'll see the Docker images come up. And so this is literally running the same test network. It's got one orderer, two peers, and you have to give it a little bit to initialize itself. Give it another 15 seconds or so. By the way, we're running this on Amazon Workspaces. It's an Amazon Linux environment. No changes whatsoever to that either. Obviously, this is done in Docker's unit test environment, but there's nothing specific to it. You could deploy it anywhere. In fact, one other useful pieces of information is the Docker image we're actually using is a slightly modified version of the one that you would download. The real difference here is strictly that we've added some directory commands, volume commands into the peers, into the peer 0 and peer, peer 0 org 1 and peer 1 org 1 or peer 0 org 2, whichever it is. And you can see that right here, that we've added commands to bring in the scripts and to be able to access the shared objects. There's literally, other than that, there's no other changes. We did that for both nodes. So at any node that's going to want to be able to dynamically load classes has to be able to access those classes either locally or over a URL or a file system or something like that.
Okay.
So again, the system's up and running. The Docker containers are running. By the way, the Docker images, do that again. Are standard Docker images. We did build these ourselves, so they're built directly from the source. If I can scroll it up just a little bit, you can see them. I don't know if I can. There we go. Like here's the Fabric orderer, and it's a 2. There's a 2.3 in here as well. There's also 2.2. And we rebuilt them directly from the downloaded sources with some slight modifications for the config to tell it to use an external chain code approach. Other than that, no difference whatsoever. Let's create the channel next. And at this point on the, let's go over to this side for a second while it's doing that. And literally we're doing this. We loaded the Docker containers. Now we're simply going to, and they've now talked to each other. And from here, we're simply going to create a channel for them to talk to. And this is, there's no change whatsoever. It's exactly the same code you do yourself. Whatever it's done in the bottom window is log into one of the peers, so then a little bit I can actually run the tail the log for the class manager infrastructure, so you can see it actually outputs some of the commands as it runs. I'll show you a little bit of source for that before we run it as well. Okay, so we've now successfully created a channel on top of the nodes running, the orderer running, everything's up and going great. We have not deployed any chain code yet. So the next thing we're going to do in the normal system is deploy your chain code. In our environment, we're actually going to deploy the foundation, which is the class manager infrastructure, which looks like chain code again. And here it goes. It does a standard install. There's nothing special to it. It returns a class chain code ID, and you can see this long string, which is a secure hash key, essentially. 32 bytes. It's doing that. Let's go look at where it gets installed to. Again, we're still using the means where it installs internally to production inside the Docker container, but obviously it could be anywhere you want. We're using the external builder approach. Here's the class manager, the chain code ID for class manager directory. Doesn't finish loading it. This build is the source. This is, of course, built in correctly. Here's the classes to be able to load. In the binary that actually go, the chain code is actually the class manager right here. That's the executable chain code that's loaded. And now it's going to do an init of the chain code. When it does, you'll see a class manager log be created in this directory. Chain code, the earlier versions of Hyperledger had a global log. Now they asked chain code to create their own log, so we did a class manager infrastructure chain code log. And we'll tail that so you can see the changes as we run them. If you notice, the last command was an args with an init that ran the standard chain code init. And there's now a class manager log. And as you can see, there's the enter and exit for the init. I believe this will make it just, now we're watching it the whole time. So at the moment, we've created just enough in the init. It actually creates these built-in classes. These are actually still dynamically loaded. So if you can see up here, class is still a shared object. Class object is a shared object. These are plugins loaded by the init code. They're considered built-in though, because they're the bootstrap, the base that you need to actually make the thing run. Class is the meta class that creates classes. Class object is both the root object and essentially the root class as well. The class dictionary is a string name to ledger object ID to be able to find the object references, and we'll show ledger object IDs or LOIDs several times coming up. Technically, this is all you actually need to make a class environment run. However, if you want a dynamic environment that clients can add new classes to in new objects and those types of things, you need a framework. This is not a framework, this is just the base requirements for a first class object model. So we're going to put the rest of the pieces together. So now that we've deployed chain code, we're now going to init the bootstrap, which loads in all of the bootstrap classes. And this is a command that's now sent as a transaction to the class manager infrastructure train code as a regular transaction, which means, of course, anything that's put in the database is replicated just like anything else. There's nothing specific here that means anything about class code. It's just running. And in fact, before we do that, let's take a quick look at some of the code it's going to run. This is a piece of the init code. It's not really relevant that all the details of it, but it's going to create a class. Creates the class by loading the class file. This one happens to be what's called XBOM container. We'll show you the class tree in a minute. This one will be the class factory. This will be a class account manager and so on. Goes down and loads all those classes up. So let's do that. And you can see down here the code, the output of it actually running in the tail. We'll let it run this for a bit. It takes a little bit to get the transactions out. Oh, there we go. So let's go to the next slide and see what we've done. We just created with the Bootstrap classes is the base application framework environment that you need to do anything useful. The init Bootstrap message and transaction is completed and has created the following classes that have been dynamically loaded from their class file implementation, shared object plugins. As you can see, there's now a full class framework. The first one, I'm just going to walk through these relatively quickly, and you can see that the arrows are showing the type, so that the classes are all of type class class, and the inheritance. You can see that class file loader, class XBOM both inherit directly from class object, and as you can see, class XBOM then creates the root for all other classes. Class file loader literally is the class type for class file loading of the plugins. So once you've bootstrapped the system, you would create an instance of class file loader and then tell it to load the class that you want it to load. That class currently expects a file system path, but subclasses of it we intend to have read from URLs or other types of searches to go find the classes. Class XBOM is the root of the entire system, and we expect everybody to then inherit from class XBOM. Class XBOM container, we'll show you what that does, but it creates a containment capability of the parent-child relationship. Class factory implements what's known as the factory design pattern, and class account manager inherits from class factory, thus creating the class account manager will create new accounts, and class account is the first account type, which of course in the design pattern class account manager knows about. Okay. There's one more thing that happens, and you'll see that as we run through this. Let me go to the next slide. In this slide, what we're pointing out is that there's two objects that are also created as bootstrap objects. One of them is known as the root dictionary, and it's an instance of class dictionary as it's shown. And root dictionary is the global dictionary that translates from string names, which could be the equivalent of path names, to ledger object IDs for the objects. Generally used to locate classes to then create instances of in the bootstrap account or system account object that you need to be able to send messages, because all objects, as will be shown in a little bit, are contained within accounts. Accounts themselves are also objects, and they essentially contain themselves. So they're the root. I'm going to now pull up the next script, which is right here. It's going to return the ledger object ID for the root dictionary. Now, this is not technically an object message. This is a transaction being sent to the class manager infrastructure. You need a couple of handful of initialization transactions that can be sent to the class manager infrastructure to get enough information actually being able to start sending object messages. We'll show you the object messages once we get through these. You can see that it ran it down below. It did an invoke. There's a standard class manager invoke as far as chain code is concerned. And it returned back a ledger object ID. This is a 32-byte secure hash, or 256-bit. We print it out in printable ASCII, so these are character numbers. Numbers turn to characters. This is actually the ledger object ID for root dictionary. Now what I need is an account object that I can send initial messages to, and there's the root one that's actually called the system account. That's part of the built-in Bootstrap system. And we're going to simply run that as well. It's going to return back another ledger object ID, and we're going to use the ledger object IDs to send an object message. And go. And there's the ledger object ID for it, right here. Returned. So we now have an account object and the object to send messages to, and we're going to now send it a message. The message we're going to send it is, get me the root account manager. Part of the Bootstrap is it actually creates this, so we know this already exists. I'm going to go to the next slide because it might help to explain what's going on as well. Sorry, that's the full, this is what the full system looks like. Next one is what we're doing here. We're about to get into creating accounts. In order to do that, I need a root account object. So that I have I need a root account manager object, which now becomes a class factory, which is going to create new accounts for me. And then we have this containment tree capability. Every account can contain objects because it inherits from class XBOM container. And if you have an object in your account that also inherits from class XBOM container, it can have more child objects, so you can make a nested tree as deep as you want. This is similar to what you'd find in a window tree. So let's go do that. Let's get the root account manager object. So I have a factory object that can create accounts. And let me do this. You'll notice that this is actually doing our first actual object-oriented message. It's doing an object send. This is the, let me highlight this a bit. This is the account object. If I scroll over to the left, to the right a little bit, you'll notice a second object, which is the actual dictionary object I'm sending the message to. Over here, you'll see I'm sending the message. The message is actually called class dictionary get object by name. And the input arguments to it are the path name for the root account manager. It's going to then return to me that object ID. Sorry, I already did it, so let's do a paste. And go. And now what it's done is returned an object handle, which is a ledger object ID. Internally, object handles are actually handles to an indexed array, but from the client viewpoint, they're ledger object IDs. And now that we have that, the next thing we want to do is actually create an account. So the very next message is, since I know that my class account manager, let me back up one. My class account manager inherits from class factory. So I'm going to send a factory message to say, make me a new instance of the class type that you're a factory for. And so that message is right here, class factory, new object. Standard design pattern approach. And let's go do that. So now I'm doing another object message. Sorry. So let's run this next script, which sends an invoke transaction to the class manager infrastructure, sends a message of this type. And we have now created an account. Here's returned, here's the handle to the account, and this is the ledger object ID. If you'll notice, this the input arguments here actually takes a count of objects to create, which would be a count of accounts to create, and I could create multiple accounts at the same time if I wanted. Each one will be returned with a unique ledger object ID, or I can simply rerun it, and there's yet another account object, and these are now being put onto the ledger exactly the way any other data would be. As far as Hyperledger Fabric is concerned, all it's doing is maintaining its database. So what I want to do next is walk through what a transaction looks like at a high level and just make a couple points about that. Okay. So when we send a transaction to the class manager infrastructure, the transaction would be an object send in most cases. It takes, the transaction expects, and this is set, of course, as JSON syntax, just like any other message, client message, but it takes a ledger object ID for the account object, the ledger object ID for the target object, the method name you're sending, it's going to method resolution, and the input arguments, which is a data structure. The input arguments, we do one for the input arguments and one for the output arguments. When it receives the message, the code, the class manager infrastructure uses the ledger object ID for the account object, to pull its instance data out of the database. It does a straight read. This is key value again. Uses the target object, ledger object ID as a key again to read the instance data for the target object out. Sets up the instance data for both of these. Then it does a method dispatch, what's known as a method resolution, and looks up the class tree to find the class code that implements the method for that object for the message being sent. It executes it, and as it executes it, your code receives its instance data in the methods. We can show you some of that code when we describe out the code for the classes. And the instance data, you modify that instance data just like you would like you're writing any other object-oriented code. And when you're done, when your transaction completes, anything that gets modified is automatically written back to the database. Your code does not get involved in reading or writing from the database. It's in fact completely transparent to it. You're literally just dealing with object-oriented code. Once that's changed, any updates to the database, now there's any keys that have new data written to them, becomes part of the write set for Hyperledger, and that gets sent to the other nodes. And it gets verified just like any other transaction. At this point, there's no difference whatsoever. Okay, so as noted in the highlights, object instance data is managed by the class manager infrastructure automatically and replicated by Hyperledger Fabric automatically. It means there's no developer interaction for this. You're writing object-oriented code. The return output arguments are, as you've seen on the right side, return just regular JSON syntax, and then the transaction ends. Actually, think the transaction ends and the data is returned. There's nothing special to this at this point. You're literally just running straight train code as far as Hyperledger Fabric is concerned, which is one of the strengths here. One additional piece, we have implemented an ability to actually read and write the database directly from your class code, where there are instances where instead of using the instance data, you actually want to read and write other records. That's fully supported. And just a real quick piece about the class structure overview, because we're going to go into that in another event when I walk through some of the code. It's not part of this particular video. A class structure overview, the class implementation code goes by the class name Go for their Go files. There's a stub file, which other classes use. There's a skeleton file, which the class manager infrastructure uses to make the method calls. And then your implementation file contains instance data definition, a method table to do the method resolution, the method implementations, other class administration functions, those are boilerplate, and then the other two files are your stub methods and your skeleton functions. Very straightforward. It's a bit manual in process, but as far as the user is concerned, it looks and acts like regular object-oriented programming. The only difference is your classes are, the class object data itself is on the blockchain, and because we're pulling the code itself from URLs or file system or mounts or anything like that, you don't get involved in any distribution issues. Once you've instantiated a class on the blockchain, any node that's doing a transaction will pull that code in automatically. So this concludes this particular presentation. Here's the contact information. Jay Moore is our contact for marketing and social programs. We have a Telegram channel, Prasaga Official, and you can hit prasaga.com for more information about where we're going with this. Please feel free to reach out to us. Thank you very much.